So good morning students. In this class we will discuss about boundary layer thickness. Okay, so what is actually the boundary layer thickness? So we have studied in our last class when a fluid flows around a flat surface or curved surface. Suppose we have taken a flat surface. This is the surface, and along the surface we have considered the direction is x and its perpendicular direction is y. So when a fluid flows around a flat surface, then in the neighborhood of the surface there exists an imaginary layer. And what is the property of that imaginary layer? That if the surface is at rest, then at the surface the velocity of the fluid will be zero due to that no slip condition. Then as we proceed along the vertical direction, its velocity is gradually increasing, and then we reach at a point where we attain the maximum velocity, and that is equivalent to the free stream velocity. Okay, and beyond that the velocity is remains same, that is of u. So this particular length, okay, or this particular region is our boundary layer or laminar boundary, and that is called the thickness of the boundary layer, and it is generally denoted by delta. Okay, so after that boundary layer thickness, now we see about displacement thickness. Displacement thickness. Okay, so displacement thickness is generally defined as the displacement of the so again I'm coming back. So displacement thickness, actually it is defined as the distance by which external potential flow is displaced outwards due to the decrease in velocity in the boundary layer. So suppose we draw this to figure. This is our real case, means where the boundary layer is formed. Okay, this is the formation of the boundary layer, and we see that inside the boundary layer, okay, suppose this is an imaginary line. At this point the velocity is 0. At this point the velocity will increasing, velocity is increasing. Okay, so this is the velocity at various values of y within the boundary layer. Okay, now we make it solid, and beyond that the velocity remains fixed. Okay, so this is the case where boundary layer is formed. Okay, this is the property of the boundary layer, and this property or this concept of the boundary layer was established in the beginning of the or 1905, 1905 by Ludwig Prandtl. Okay, so somehow it is also known as the Prandtl boundary layer theory also. So this is the real case. Now if there is no formation of boundary layer, or if there is no boundary layer, then what will happen? Then the region will be fixed. Okay, this will be the case. Okay, this will be the case if there is no boundary layer, means for various values of y you are getting the same value of u. Here you are getting that the values of velocity is changing, but if there is no boundary layer, the velocity will not be changing. For various values of y, you are getting the same velocity, that is of capital U or free stream velocity. And suppose here the velocity is small. So this is the case of with boundary layer, and this is the case of without boundary layer. Okay. So now what will be the definition of the displacement thickness? So displacement thickness means it is a distance by which potential flow means there is no boundary layer, is displaced outwards due to decrease in velocity in the boundary layer. So means what happens if you see that here small u is less than capital U. How? Because just in the definition of the boundary layer you have said that the velocity raises from 0 to maximum velocity capital U within that boundary layer region. So small u is obviously less than capital U, but if there is no boundary layer, all the velocity will be same, that is capital U, where capital U is greater than small u. So thus what we have seen there, due to the formation of the boundary layer, the velocity of the fluid is reducing. So if the velocity is reducing, so there will be some mass flow reduction in some mass flow rate. So the displacement thickness is generally connected with the reduction of the mass flow rate. So now we will see how the mass flow rate comes into the picture. So in a side note, we will see about the mass flow. So suppose this is a structure so this is dy, this is dz, this is dx. Okay, the fluid is moving along this with the density rho. This is the direction and u is the velocity of the fluid. So rate of what we need the rate of change of mass. Rate of change of mass. So rate of change of mass equal to what is the mass at this surface. Suppose we name this surface as second surface, this is the first surface. As the flow is along this direction, so the rate of mass at this direction will be rho. Okay. Then what is the volume? Okay, volume will be, suppose the coordinate of this point is x, so this distance is suppose x from a fixed point O. So this is x plus dx into dy minus dz. Okay, minus what is the rate of mass at the surface 1. So this is rho x dy dz. Or what is the mass at this point? This is the mass at the second surface, this is the mass at the first surface. Okay, now rate. Suppose the time taken from this point to this point is dt. So this two part is cancelled, so it is rho